Hello, good morning, everyone, and thank you very much for attending the second session, the Q&A session. Thank you to all of you that sent out the questions, but this session is intended to be completely interactive, so please feel free to ask any questions. Perhaps you is taking a week to digest the first intro session, so you have more questions that you haven't submitted in the form. So here is the forum just to ask any question to all our subject matter experts. So the session is going to be, we're going to start with responding all the questions that you send us. Then we're going to give you some time just to ask any questions as well. And you might have seen it in the agenda that I sent out yesterday. We are going to, let me one sec. I think I'm going to mute. Okay, I'm going to mute everyone. There was some background noise. So I'm going to have we're going to give a space to ask more questions. And then we are going to give 3 presentations as per the feedback that you've got and the questions that we got. We are going to present PyGeometry, PyCMAI, and the PyPrimeMesh. So yeah, I hope you enjoyed the session and you find it fruitful and interesting. So we are going to start with all the questions, just in case you had a question that we already answer. And then once we finish, we go around 15 questions. As I said, we'll give you time, raise your hand or just jump in to ask any questions. So can you all see my screen?
Yes, David.
Yeah. Okay. So we're going to start with the first one. So first one, PyAnsys use demo on a Workbench mechanical project. Launch of PyAnsys from Workbench, write and execute code. Show how to run several repetitive simulation with PyAnsys on Workbench mechanical. Pierre?
Yep, I'll take that one. Welcome, everyone. This question has several answers, and I was not sure which direction to take. So what I want to remind everyone, and probably you've seen that already, but when I see a question like that, I'm always wondering, okay, do you want to run like design points out of mechanical and Workbench, or do you want to run that from outside? And that's still the question. So that's why I kind of start with reminding everyone that there are 2 ways to look at scripting in at least in the mechanical work, which is the one I know the best. One is in product scripting. So you have the Workbench scripting, you have the mechanical scripting, you could have space claim, you could even have things like an APDL. So that's one possible answer to that question. The other one is when you do scripting from within your own tools, or let's say outside of the Ansys products. And then that's where PyAnsys kicks in, because you are going to use PyAnsys to call your either mechanical or Workbench or whatever. So if you go to the next slide, David,
yeah.
Go into some more details. So if I had to answer that question of show me how to run, a mechanical simulation where I change parameters, where I run several design points, this is the way I would do it if I was in plain in product scripting. So using basic Workbench project page scripting and mechanical scripting. So the way I would do it, I would create my mechanical model, create my parameters, and then, run design points like you have on the upper right of the screen. So I run that script from the project page and I update my parameter, update the values, get whatever I need to do. So that's one way to do it. And I'll come to it again later, if I want to use changes in the models that are not through the regular classical P-box type of parameters in mechanical, then I probably would have to send a script to mechanical to update something different in the model. And then I can use this model 1.send command type of command here to send something for mechanical to do. So, but all of that here I'm showing could be done within the product. So there is no PyAnsys involved. This is just plain regular workbench page and mechanical scripting. Now, if we go to the next page, we could do it differently. Of course, we could use PyAnsys, but then again, I'm stepping out of the products, and then I can launch Workbench. From Workbench, I can start a mechanical session through. So what you see here is regular Python scripting. So again, you do that outside of any of our products, and you drive everything from there. So that would be the base syntax to start Workbench and start mechanical from Workbench after you've loaded the geometry and you start doing stuff. And obviously, you will send scripts to mechanical. So the script as itself on the screen, won't do anything because you don't have everything. But I was just wanting to highlight the main lines you would need to start Workbench first, upload the geometry, start mechanical as a server, launch mechanical, and then send anything you want to mechanical to set up your model or to modify your model, because here we are kind of starting from scratch, but you could open an existing project and run that. So that's another way to answer that question. If we go to the next slide now.
Yeah, just one thing, like we will be sharing, so you'll see some URLs. So we will be sharing these slides. So no one, please, no one write it down.
I'll put references wherever I can. So if you want to run variations with mechanical, so the first one, as I said, is the in-product method. So you use Workbench parameters. You pilot from the project page or from mechanical, because from mechanical you can call the project page. That's one way to do it. Second method, which you could use for both in-product or PyAnsys, is to change any object value in mechanical using a mechanical script. And in this case, you could skip entirely the definition of parameters. So you don't have to check the parameters. Fundamentally, you can change anything with that method in mechanical. And that's a way to use parameters which are not available. Let's say you want to parameterize the ball pretension. That's not available by default in mechanical. So that's a way you could do it. So, and there is an example here that I linked on on our forum. The third method would be to retrieve and change the parameters using PyWorkbench, assuming you've created those parameters. And what I don't have for today, but I'm looking for right now, is a way to drive those parameters in a mechanical standalone, where you don't have the project from the Workbench page, you just have a mechanical session, and you can change those parameters. But I don't have the answer yet. I've asked a few colleagues to help me on that. So fundamentally, as I say, one question, multiple answers, but that's the nature of scripting. There is usually not one single solution. So depending on what you want to do, this may not be PyAnsys solutions. This may be just Workbench and mechanical scripting. Or if you really want to drive that from somewhere else, yes, that's going to be PyAnsys, and in this case, probably PyWorkbench and PyMechanical. That's it for this one. Again, use the chat if you have additional questions that we could answer.
Thank you, Pierre. Building a clean automatic geometric recognition between PyAnsys geometry and PyMechanical. No loss of instances, name selection in Python. Berto?
Yep, I'll take this one. Okay, so this is a very typical use case, especially when you're starting to consume the PyAnsys libraries. On the screen, we have two screenshots. The one on the left is the PyAnsys geometry script, and the one on the right would be what you would do in PyMechanical, for example. So with PyAnsys geometry, you can perform all your modeling operations. You can create your geometry from scratch. You can import certain geometry and create your name selections as you move forward. In this example, we are basically creating a set of boxes and extruding them. You can basically see the sketch that we generate on lines 5 and 6. It's basically a box. Then we launch our modeler, which can be SpaceClaim, Discovery, or the geometry service. And then we are extruding that sketch and translating the outcoming boxes into different locations. And finally, we are creating some name selections in lines 25 and 26. Anyway, once we have our geometry, we can make use of the export to PMDB file, which will download to our local file system a PMDB file. Now, PMDB is a native format for mechanical, and it will contain all the name selections that we create, as well as the instances and so on. And then you can easily pass it over to mechanical and read it using the code snippet that you have on the right. So that would be a way to combine both of these libraries, PyAnsys Geometry and PyMechanical. Now, we also have combination with other libraries like PyFluent. For example, with PyFluent, you can also consume this PMDB file, and it will contain all these name selections as well. For PyPrimeMesh, where we also have support for different file formats like the step file or the FMD file, and we also have those export functions on the geometry side. So feel free to export the different export methods we have depending on your needs. And yes, you can see on screen the demonstration on how to combine both of them. That's it, David.
Thank you, Roberto. Next one, during the first session, it was mentioned that DPF can also be used for pre-processing. I noticed in the examples that a mesh can be generated, but can you tell a bit more about possible pre-processing capabilities of DPF core? Like if it is possible to define and assign materials, element types, boundary conditions, solve, etc. Paul?
So yes, I think... Oh, Pierre, you want to go?
Paul, up to you.
I'll go ahead then.
Yeah, so here, you shouldn't think that DPF is going to help you, create like materials, contact solving, and so on. That's a fully different purpose. DPF is really for manipulating, large amounts of data efficiently and so on. So there are many things you can do for pre-processing. So I'm not saying this is only post. In pre-processing, you could use DPF to create complex fields. You want to, get some results, manipulate them, use them as binary conditions. So that's typically a good use of DPF for pre-processing. But then you will have to write, the data for the solver. And typically that's where a Python code object in mechanical would help. So easy one to do. On our end, we are also using DPF for pre-processing when we do external data. So you will see many changes. Some have started with 24R2, but we are doing way more with 25R1, where instead of writing all of the SF, BF type of comments to the APDL file, we are going to use DPF as a way to, extract the data at solver time from a file and so on, which will reduce that. And finally, another way to think of pre-processing with DPF in terms of operations. It's kind of related to the first one, but that's where you could do mapping. You have data that you want to map from one mesh to the other. So those operators are available in DPF and could be used to do some sort of a mapping and, sort that out to the solver file again. I worked with a customer recently in mapping results from different stages using kind of super elements, things like that, mapping onto different meshes. So all of that could be done and would be how I would use DPF for pre-processing. But again, no, it does not let you assign materials, element type, boundary condition. This is not PyMAPDL. This is not PyMechanical. Paul, anything you want to add to that?
Yes, basically what may be easy to remember is that PyDPF or DPF does not currently enable you to write input files for Ansys solvers. That's where you use PyDyna, PyMAPDL, and things like that. So anything you would see in an input file, like normal commands, like definition of element types, boundary conditions, and such, we do not do via DPF.
Thank you. I saw a hand. I think it was Saint. I don't know if it was by mistake. Any questions, by the way, while we continue about what we discussed? No? Okay, we continue. Okay, next one. Can you speak about the future plans regarding the machine design toolkit in AEDT or other toolkits? Will the functionality be integrated into PyAEDT? Julia?
Yeah, thank you, David. So that's mine. So it's not specified here which machine design toolkit you're speaking about, because it could be referenced to the machine toolkit to create performance map or the EC machine toolkit in ADT. So if it's the first case, we tend to use the MotorCAD lab link in order to drive the Maxwell solver from MotorCAD, and the data can be subsequently extracted and post-processed in MotorCAD. So that's the first case. Regarding if this process can be automated, not for now. It might be from version 25 R1. But of course, the API is not tested yet, so there's nothing sure for now. The functionality is there, so not in PyMotorCAD for now. If instead the question was referenced to the EC machine design toolkit, we're not planning to integrate it into PyDT, and we don't have further details about that. Of course, if the intention is to sweep current and voltage, you can use PyDT and then subsequently get the map data. So these were the two cases that I was able to cover regarding the first question. One thing that I wanted to highlight here at the bottom is that maybe this question arises from the fact that I mentioned PyDT toolkits. So what we call PyDT toolkits are something completely different from the old ACT toolkit. The PyDT toolkits, as I mentioned here, are more complex workflow where we implemented both a backend and a front-end part. For now, we have two open source toolkits, one for high frequency application, the antenna wizard that allows you to design antenna, and another one for low frequency application for the magnet segmentation to segment and skew magnets. These are accessible through ADT, through the extension manager that I show in the previous presentation regarding the installation of PyDT and extension manager. So yeah, that's it on my side regarding these questions. Hopefully I covered the questions here. If not, yeah, ping us and we can go further into details.
Thank you, Julia. Next one, you mentioned something about extensions like PyCalculator. Is that something like a package for the fields calculator for manipulation of field data? I think this one is for you, Julia, as well.
Yeah, so that's mine as well. So I will start speaking about the PyDT Advanced Field Calculator. So you have to think about the PyDT Advanced Field Calculator as a tool that functions as an extension of the existing ADT fields calculator. Again, you have to think about it as an extension and not as a replacement of the already existing ADT fields calculator. Because this new PyDT fields calculator provides an additional pool of custom expressions that are appropriate for each solver you're accessing the calculator from. So these expressions can be used with the ones that are already available in the ADT fields calculator. So like the combination of the two libraries gives the user like a convenient way to accessing frequently used quantities. I put two screenshots here. As you can see on the left, the advanced field calculator, it's it's an extension that can be installable through the extension manager. And there are two ways of adding expression in ADT fields calculator. The first one is from what we call expression catalog, which is none other than a TOML file, where we already implement the most frequently used expression depending on the solver. Or second case, you can add a custom expression without going through the expression catalog. For example, you can add your expression as a dictionary and then use a proper method to add an expression. Now I'm gonna show you to you in a second. In fact, on the right, you see that through AEDT, you can access this advanced field calculator. We implemented a very simple UI that is able to detect the type of solver that is activated. And then depending on the solver, you have a list of calculation available. And these are the calculations that are already available in PyDT. Now, let me quickly share the screen to you. I will still the screen, David.
Sure.
Okay, do you see my screen?
Yes.
Okay, so just as a reference, this is the main page of PyDT. If you go to user guide, extensions, and advanced field calculator, here there's the description on how we implemented and the available expression in the expression catalog TOML file. This is how we define expressions in our catalog, in our TOML file. As you can see, we provide the name and description, the design type, so the design where this specific expression will be available within AEDT, and then here the list of available operations, the list of operations that define this specific expression. And again, these expressions are available already in AEDT. And again, this is the same screenshot. Depending on the solver, you will find a list of available expression. The second way of adding an expression is these. One sec. It's this by using this method called add expression. What does it require? So here you have an example. You can add your custom expression without implementing it in the expression catalog. You can add it on the fly, basically. It's a dictionary. The key of this dictionary are exactly the same keys that are in the expression catalog. Here you define the list of your operation, and then what you need to do, you simply have to pass this expression to the add expression method. And if it's needed, an assignment, as it is for here, you select the geometry needed to compute this expression. Okay, so these are the two ways of interactively using the field calculator. Okay, so David, this is the first question. If you can share it back, I will quickly introduce the second. Okay, the second question. So the second part is about manipulation of field data. So we recently implemented a new way of visualize field data in PyDT. I put here the link. This new way of visualize data in PyDT allows you to manipulating data inside and outside AEDT. For manipulating field data, PyDT leverages PyVista package that allows you to manipulate 3D plots, and there's a class in PyDT called Model Plotter that allows you to manipulate data. Now, I can quickly share with you. Sorry, David, I have to share it back. I have a very quick demo. Sorry. So I'm running a very simple example. This is a DC conduction analysis. We don't care about the application, but I just want to show you how you can, in this specific case, plot an electric field using PyVista. Okay, so we have this method to plot a field. Here you can decide whether to show it or not as a PyVista plot, and then afterwards you can manipulate the PyVista plot through PyDT. Okay, let me run this. You see a new window pops up, and this is your. Can you still see the screen? You see the PyVista plot? Okay. So this is the PyVista plot. This is And this is the object that is returned here, the PyVista plot. If we evaluate this plot, you see that this plot is a model plotter. This is the PyDT model plotter that you have to think as a wrapper of the PyVista of the PyVista plotter. In fact, one of the property that is part of this model plotter is this PV. This PV represents your PyVista plot. And you see, in fact, the object type. And from here, from this PV, you can access all the data of the PyVista plot and manipulate your field data. Okay, so there, hopefully I answer to all the questions. Again, if there are further questions or doubts, ping us.
Thank you very much, Julia. So
Thank you.
we continue. Oops, the next one. What about internal scripting methods, VBS and IronPython in AEDT? Since the start of PyADT, there have been rumors that this will be die out at some point. Will this happen with 25R1? Are there any plans?
I will answer this one, David. So there is no plan to deprecate VBS or IronPython in AEDT, so no worries if you are still using IronPython in AEDT. But the plan is starting the deprecation in 26, but it will not be total deprecation. It means that if you are using the AEDT API, you will be able to use CPython because the plan is migrate the interpreter of the electronic desktop to CPython. Currently, as you mentioned, it's IronPython, the one, and is the problem of IronPython is that it's frozen in Python version 2.7. So all the new features of Python, all the new efficiencies are not compatible with this Python 2.7. For that reason, future version of electronic desktop will migrate to CPython version for sure, but it's still in the AEDT roadmap. But once I said that, moving your scripts, your workflows to PyDT, we think is the safest approach right now, because if something changes in the electronic desktop, if you're using PyDT, you will be always compatible with the electronic desktop, because at the end, if something changes, PyDT will also perform this change in the electronic desktop. Not only that, we will explain this I think, in another slide, in another question. But at the end, PyDT gives more flexibility for adding new features. Also, if you find any problem, any issue, or you want to add a new feature, it's just a matter of submitting an issue on GitHub, and the community will help you. But as you know, if there is something that is not working in the API, you will need to wait at least 1 year until the new electronic desktop release is launched. So we think that moving to PyDT is right now the best approach.
Thank you, Samuel. Next one. As I understood, PyDPF is a post-processing tool for mechanical. Is that correct? Is there a way to also use it with AEDT? And if yes, what can you do with AEDT data? What are the benefits? I think Paul will respond to this one.
Yes. All right. So first part of the question, as I understood, PyDPF is a post-processing tool for mechanical. Well, again, it depends on what you mean. The PyDPF libraries provide access to the DPF Ansys data processing framework. And so in that sense, yes, it does enable you to do some post-processing on, let's say, mechanical result files. So you can see on the right, I put the list of supported file formats for now. So we have EMEA file formats, LSDyna, but we also have some Fluent and CFX file formats. Also be aware that, as Pierre mentioned at the very beginning, it really depends on what you mean by for mechanical. If it means from within mechanical, from within the mechanical UI, then what you are going to use are Python scripts, I think, which are in IronPython, and it's a different API. It's not PyDPF. So PyDPF is for when you interact with results coming from mechanical, from outside mechanical. And so you have the list of supported files again on the right. And as for the second part of the question, is there a way to also use it with AEDT? So with AEDT result files, as I understand it, sadly, the answer is no. This is what we are working on and what we are preparing for next year, I think. So this is planned. This is obviously one of the things that we lack at DPF. It is support for electromagnetics result files. So this is planned. So the answer is no. And what can you do with AEDT data? What are the benefits? So of course, there's going to be a discussion to have between whether to use PyADT directly or whether you have some benefits to use PyDPF in addition to PyADT. The answer is PyDPF basically gives you access to the DPF framework with all of the operators and ability to create complex workflows for filtering, serialization, and more. So we're also, of course, going to be developing operators, specific operators for the kind of operations you would want to do on results from electromagnetic simulations. So this will most likely come with the support of result files from AEDT. Sorry. So I hope that answered the question.
Thank you, Paul. Okay, so we go to the next one. So what is the general approach for meshing with PyPrimeMesh? It seems to me quite different from meshing in mechanical, where a general mesh is made to the whole object and then further refined. Is it possible to create the same procedure in PyPrimeMesh? This file only managed to create the mesh by meshing each phase after another with the specific options. Alex?
Hi, can you hear me?
Yes.
Hi all. So the approach for meshing in PyPrime might be a bit different from mechanical. You have to consider that PyPrimeMesh is a measure for all the products, not just for mechanical. We have a couple of ways of meshing in PyPrime, because PyPrime is a low-level library to say, so you have a lot of fine-grained controls over meshing. But we also provide a kind of high-level meshing for the most general cases. So we have two examples here. One is using the Lucid model, which will be the high-level model for meshing. And yeah, you can see the code is just really reading an object from geometry from one of the libraries, and then just dot mesh, and that's it. And if you need to have a more fine control over the meshing, you can use the surfer class to do this. And in the surfer class, you will need to declare some parameters for that meshing, and then apply that meshing to the phases as you were doing in your example. In any case, if you're using the fine-grain class to do this, you can pass the list of the phases. You need to do it phase by phase. And yeah, that's mostly it. I just maybe want to highlight that we have that high-level meshing library, the Lucid meshing library, and that is included in PyPrimeMesh, of course. And that might be closer to your experience with PyMechanical. I hope that clarifies the question.
Okay. Thank you, Alex. Just to remind, Alex will be just providing a presentation about PyPrimeMesh. There will be the third presentation, so we'll deeper in the topic. Thank you, Alex.
Thanks.
Oops. Okay, next one. I like to be able to encapsulate simple simulation, calculating the stiffness of a pair of sunglasses, for example, with Python code while being linked to an in-house web interface.
Yeah, I can take that one. So here, well, the question describes exactly the purpose of PyAnsys. So you have created, like a very repetitive simulations that takes some geometry inputs, some basic, load type of inputs and so on. And you want to run that, either using mechanical or APDL. That doesn't really matter. You're going just to use PyAPDL, PyMechanical, or PyWorkbench to do that. So you really have a choice here of the web UI. And again, you can look at some examples. So we have links in most of those pages that will refer you to that. So fundamentally, all you need to do is to have your web UI based on whatever you want to base it, and have your APDL or mechanical model ready that it will drive through PyAPDL and through PyMechanical. And usually that will always be the same, like launch whichever of the two, call your script, get your results in one way or the other, and expose that in your web UI. So that's really a fundamental thing. And again, you have a link here to a couple examples of what that could look like with PyAPDL. But if it's mechanical, that will be very, very similar.
Thank you, Pierre. Next one, how to install PyAnsys packages. Roberto?
Yeah, so PyAnsys packages are simple Python packages, and just like any other Python package, you would use either pip or conda. In this case, PyAnsys packages are delivered through PyAPI, so we recommend the usage of pip, of course. Now, there are two main options. The first one is to install all of them together with our bundled package or meta package called PyAnsys. And then in that case, we recommend that you target your specific release. That specific PyAnsys meta package is following calendar versioning. And as you can see, we specify the version that we are interested in. So for example, with pip install PyAnsys 2024.2, we will be installing the corresponding PyAnsys packages that are known to be compatible with 24R2. However, PyAnsys packages, they follow a semantic versioning scheme, and then they can do more frequent updates than the Ansys product releases, which they go out every 6 months, and they will still be compatible with previous versions as well in most cases. So if you're interested in installing the latest version of a specific package, you can go to option 2, in which you just say pip install and your specific package. In this case, if you want to install the latest version of PyMechanical, you would do pip install Ansys Mechanical Core. We also have to differentiate between the Python package name, which is Ansys Mechanical Core, and our library name that we provide to the repositories, which is PyMechanical. Whenever you want to install a PyAnsys library, make sure that you're using the correct Python package name, because otherwise it can lead to problems, of course. And always feel free to check the documentation of the different libraries. Most of them have tables that show you the support that a specific PyAnsys version has to the Ansys releases, and that way you can tailor your install the way you need. And that's mostly it, David.
Thank you, Roberto. Next one is for you. Okay, so we jump to Fluent. Someone was interested to access the Fluent API to programmatically solve heat transfer, and I wanted to know about CFD problems. Pablo?
Can you hear me?
Yes.
Yeah, so to access PyFluent API is pretty much the same procedure as you would use for other Ansys products. So the first thing is to go on GitHub and find all the documentation that we have there. We have in the link provided there, you can find information about how to get started with PyFluent, how to download the API, how to download the libraries, how to start creating your own cases. It's full of documentation there. So the first step would be to go into that link and then follow the steps indicated there in terms of how to install the libraries. Once you have them installed, you can invoke the library as any other PyAnsys package and start using the objects that the library provides to automate your workflow. As for the second question, solve heat transference of the problems. This is quite generic and standard. So basically, it encompasses anything that enables or is affecting energy. So I have added here a way of adding energy. It's extremely simple. It's a very Pythonic way of adding that property. Basically, the user has to start the session directly from PyFluent or hook to an existing session. For example, if the user has started a Fluent session, it can create and start the server so that we can connect from the PyFluent client. Once we have connected, either by launching it directly from PyFluent or from an existing session, you can retrieve that session as a PyFluent object, and then you can simply navigate through the different objects and classes to enable energy in this case, right? So here you have an example of how a user connected to a session can find out and enable energy, basically using the settings API, navigating through setup, models, energy, and then when it comes to energy, just enabling, setting the enable flag to true. That is quite straightforward. Then the user will need to set up boundary conditions, in this case, thermal. I'm just reverting to the simplest way, right, to set up a CFD problem. Obviously, there will be other boundary conditions, cell conditions, other effects, but the paradigm is the same. It's just navigating, it's grabbing the parent object, in this case, boundary conditions, and then navigating velocity inlet. If we have one inlet that is called inlet, as you can see in that object, then we can access to the thermal and temperature properties and set up the correct value. So with this, we can enable energy, but as you can imagine, this is the same process to set up velocity or pressure of mass flow rates or whatever we need.
Thank you, Pablo. Next one, how can I start writing my PyFluent script? How can I find the right comments? Pablo?
Yes, this is a question that comes along a lot. Because once the user confronts or follows the recommended steps at the beginning to download the library, load the library, maybe you have done a couple of examples, then you're facing your real problem, right? In your real problem, you have to perform a lot of settings that you haven't seen in any of the examples. That's most likely the case. So you're confronted with the question, how can I progress? How can I find the right objects? How can I find the right commands that I need to issue to have my automation done, right? I know how I want to set up my case manually. I know what are the steps I would do manually if I had to set this up. How can I translate all this into an automated running script? So there are a few ways. You can see them here in different steps, action steps. So they are ordered. I would first go to the first step, second step, and third step. The first way, when you're confronted with that question, would be, okay, is this set of actions that I want to do, or are these models that I want to enable and set up available in the Fluent Web UI? If that's so, what I would do is to start a Fluent Web UI and connect to that session, or start the session, connect to a Fluent Web UI, and then perform all the necessary steps for your case, for your automation in Fluent Web UI. Once you do that, all these UI operations, you can record them into a script. There's a flag when you enable a Fluent Web UI that allows you to print a script that automatically records all your actions in the UI as a settings API Pythonic script. So it's a ready-to-use script almost, or ready-to-use script. At least, or in the list, you can look at the written script and grab a lot of information from there about what are the objects. So for example, if manually I go and I change a property in a boundary condition, or I change the number of iterations or create a report or things like that, you get the corresponding action scripted in this recorded script, and then you can just copy and paste it in your own script. So this is a massive source of information that you can have very quickly, and converts what you are doing, action items you are doing manually, converts directly, translate them into Python. And from that sequence, you can learn a lot. The Fluent Web UI is not fully completed, so there are a lot of models, as you can see. The original Fluent UI has thousands of different options. Fluent Web UI doesn't have all those many options. So if you are trying to set up a model of a submodel or a submodel, probably that is not in Fluent Web UI. So then you have to go to the second step. Whenever these methods are not available in Fluent Web UI, what the user can do is find the corresponding journaling script commands. So probably, in standard Fluent, you have commands in the text user interface to invoke any action that you would do manually or invoke any model. If you find that command in the journal, then you can have an automatic export from that command to the corresponding PyFluent command. And that's very easy, because if you have a script that makes a set of actions in journaling mode, you can invoke the 2Py argument when you launch a Fluent session with that journal, and then it gets automatically writes down the corresponding PyFluent script, so that you can grab exactly the same information as with the Web UI, right? And that works for every single command that is in journaling. Therefore, every single command you can use in Fluent to control an Fluent session. And finally, there is a third step for all those remaining methods that are not covered by the first step and second step, which hopefully are very, very reduced, and over time will be even less. And it's using built-in methods that are provided to the user to capture different information about the methods. For example, allowed values allows the user to know what kind of arguments of a non-documented function is accepting, or some of functions that haven't been migrated yet or implemented yet, they can consume. And as a final piece of advice, what I would do is I would start a Fluent session with the GUI open, and then open a PyFluent script and hook that PyFluent script to that open session, and then start questioning when I do operations in the manual operations in the UI. Question how that is affecting my PyFluent objects, and from that information I can extract a lot of data and a lot of details about what a PyFluent call or function does to the PyFluent method.
Thank you very much, Pablo. So next, can I launch PyFluent on my local desktop, for example, Windows, to run geometry update in SCDM Disco, and then run a simulation on a cluster or HPC machine?
Yes, this is another question that comes along very often, because standard space claim and Discovery don't run on Linux, and many people want to leverage their HPC machines on Linux. So they want to, maybe if they are doing a parametric analysis, they want to change the geometry on a Windows machine. Can be their local machine or can be a remote desktop Windows machine. Once that geometry gets updated, do the mesh and set up in Fluent on the remote machine on Linux, run there, bring back data, and then make a geometry change, and so get into this loop. And there are different ways of doing this. The first one would be launching PyFluent using launcher scheduler options. So when you trigger PyFluent, you can provide arguments to launch PyFluent remotely, directly from your local machine. The feasibility of that depends on your connectivity to the remote cluster. So you need to have port open so that you can communicate. You should have visibility of the running machine or of the master node. But if that all is in place, then you should be able to start the PyFluent session from your local desktop, and that will outsource all the calculations to the HPC. Then there are other ways, for example, using a HPS or PyHPS, and then you can distribute the works remotely. And then there is a final way of doing it, which is using third-party libraries such as Paramico that allows you to issue commands remotely and perform actions remotely. So you could actually issue commands to run the session remotely on the Linux cluster and then bring back, run the simulation, bring back the data back into your local machine.
Thank you, Pablo. We'll go to the next one. How can I run legacy codes on PyAnsys and integrate LSDyna in PyAnsys workflow? First, there is a question. Herman, wait a sec. Gopi, you've got a question?
Yeah, Pablo, can you give me, is there any examples for run the PyFluent script in the cluster machine? Is it available currently? I searched in the PyFluent documentation, but it is a bit confusing. Is there any tutorials or related examples are available in the PyFluent documentation? Can you give me, if possible, show it to me?
Yes, Gobi, we have a couple of internal examples about how to do that. Depending on your case scenario, I can guide you on which will be the best option. So we can connect offline and we can look at that.
Yeah, okay. Because I seen that scheduler option and all, it is a bit confusing, and while we are doing in the offline as well, it is confusing in Fluent as well. So by integrating the Python, it is more, I think, critical. So it will be helpful if you show me or connect with me on offline or anytime after the session.
Yes, I will ask it a bit. But yeah, sure.
Yeah, okay.
Thank you, Gopi. Thank you, Pablo. So coming back, how can I run legacy codes on PyAnsys and integrate LSDyna in PyAnsys workflow? Herman?
Hi, thank you, David. I have split this question in two parts, basically. First one is running legacy code. There are different tools. Each library has a different method, basically very depending on the kind of product that they are coupled with. For example, PyMPDL has the option to run the input string, so you will have your commands, your MPDL command as strings, and you can input directly using mpdl.input strings, or you could just point to a specific MPDL file with APDL code, and you will read it using mpdl.input. You have a link there on how to run those files, those examples from the documentation. Additionally, for example, PyMPDL has a converter, so it will convert MPDL code to PyMPDL code, and the link for that part of the documentation is there. Other libraries like PyMechanical, they have different methods, like you could run Python script from a file using the method that is on the screen. Other libraries are more specific. You can probably ask in the chat here for any specific library that you're interested in. If not, you can always go to the Ansys developer portal and ask there, or maybe go to each library documentation, because it should be presented there, a way to interact with with the legacy code. Regarding running LSDyna, running legacy code, you can follow the example the code snippet I put on the screen. You can run basically input deck files in Dyna, in PyDyna. I have also attached the documentation, the links, and it should be possible to run legacy deck input files using PyDyna. And regarding integration of PyDyna with the Ansys workflows, we don't have any specific examples coupling PyDyna with other PyAnsys libraries. I don't think there is either an example coupling with other PyAnsys tool, except PyVista, NumPy, and things like that. Because PyDyna is, I would say, it's relatively recent library, so we are still working on the documentation and the examples and things like that. But the examples that we have already shows how to interact with PyDyna in a Pythonic way. So obtaining results through PyDyna and maybe do some plots using a plot lib, or either exporting some data and put it in pandas or maybe in your web UI. It should be relatively straightforward for people who are familiar with Python programming language and they know the basis of Dyna or LSDyna. So I would recommend to have a look at the sample on the documentation, because probably it will be a good starting point for coupling PyDyna with other PyAnsys workflows. I think that's all. David, thank you very much.
Thank you, Herman. So we go to the next one. PyAEDT differences to the old IronPython interface.
Hello, can you hear me? Because I think
Yes.
before, okay, great. So it's a similar question compared to the previous one, but here I would like to show what are the advantages of using PyDT versus the native API. So first, moving your IronPython scripts to PyDT first gives you the power of CPython. So it means that you can use the full ecosystem of open source. So that could be from NumPy, PyVista that was mentioned before. So basically with IronPython, we were not able to use all this ecosystem of open source libraries, and now with PyDT is possible. Apart from that, so how PyDT it's written, the syntax is much readable and much easier to understand. So if you compare code between PyDT and the AEDT API that I will show you later in the next slide, you will see how easy it is to understand the syntax. Apart from that, PyDT also allows to easy access to any IDE, that is the software that you are using for doing your program. So before with IronPython was almost impossible to use any IDE like PyChart or Visual Studio, but with PyDT it's quite easy to just create a Python environment and just write your code. So if you go to the next slide, David, you can see here just pretty simple. It's just the creation of a box inside the electronic desktop modeler. You can see in the left the native API, so what we can call the IronPython API. So this is just an example of how to write and create a box. So you need more than 20 lines of code just for creating the box. But with the PyDT syntax in the right, with just one line, that is this create box, you will have exactly the same outcome. Apart from that, the PyDT API is object-oriented, so it means that everything returns an object, and then you can manipulate these objects. The AEDT API, the native one, is not object-oriented, so it's quite difficult to manipulate the different objects, boundaries, excitations that you create. So I think that's a lot of reasons to move your codes to PyDT. That's all.
Thank you. So last one, status of PyCFX.
Yeah, there isn't much to say there at this point in time. There is for turbo machinery workflows, there is some work done, and especially some work done on PyTurboGrid to leverage TurboGrid to get right meshes. That is already available in the common PyAnsys repository. From PyCFX, there is not much, and definitely is not even closer to the level that PyFluent has in terms of APIs. So probably in the future we will be able to disclose more information on this.
Thank you very much.